I'm joined by Dr. Daniel Swain of UCLA's Institute of the Environment and Sustainability. Daniel's well known for his blog, Weather West, which I encourage you to check out at weatherwest.com. And he's also known for his research into the impacts of extreme weather and climate events like the ones we've seen this summer and increasingly over the last few years, thanks to human-caused climate change. His science communication work helps both journalists and the public understand both the causes and effects of the extreme weather events we witness on the news, and sadly, oftentimes firsthand. I'm really excited to speak with you today, Daniel, and especially in light of the way weather has been grabbing headlines recently. So as we speak, Hurricane Idalia is lashing Georgia after making landfall in Florida just hours ago. Now, a hurricane in the southeastern U.S. isn't usually extremely noteworthy, but it seems to me that this one has a few unusual characteristics. Can you explain a bit more about the significance of this particular storm?
Well, thanks for having me, first of all, on the podcast. And, I think this is an interesting summer to be talking about weather extremes in a warming climate because there have been so many of them in so many places, and this is the warmest summer on record in the world. We have not seen in the modern instrumental era a year warmer than this year. So what better time to talk about weather extremes? In terms of hurricanes, or collectively tropical cyclones, let's call them, because that encompasses the hurricane-like storms that occur all over the world in different ocean basins, there's a few things that we already can connect pretty clearly to climate change. And that is that the maximum intensity of these storms, so how strong the strongest winds can potentially become, how low the lowest pressures can potentially become, are increasing in a warming climate because the oceans themselves are warmer than they used to be, and warm tropical oceans are pretty literally fuel for hurricanes. No warm tropical oceans, no hurricanes, but it also works on a sliding scale. The hotter they get, the higher theoretical maximum intensity you can get with terms of hurricane winds and very low pressures. That's sort of effect number one. The second factor is we know that the rainfall associated with tropical cyclones is increasing in a warming climate. So the really extreme rainfall that you can see from hurricanes in some places, or even tropical storms that stall out for a long period of time, is increasing at a pretty rapid rate. In fact, it may be increasing in many cases at a rate faster than that of rainfall from other types of storms. So that's a sort of factor number two. The third is that what we're seeing in some basins, at least, and this does include the Gulf of Mexico, so this is directly relevant to what is unfolding today with Idalia, is that hurricanes and tropical storms are intensifying in some cases more rapidly than they used to. So not just becoming more intense at their upper end, but also becoming that intense at a faster rate, which is pretty important when you think about what just happened, for example, today, when we have what was a couple days ago just a tropical storm with sustained winds under 70 miles an hour, and which rapidly transformed itself amid record warm ocean temperatures into a Category 4 out of 5 storm with winds of over 130 miles an hour by the middle of last night. So that's sort of factor number three. And the last one, I've saved for last. In some ways, it's the most important, but it's also the most obvious, which is that the oceans themselves are rising in a warming climate. So even if we had the exact same hurricanes that we used to, but the ocean levels were higher, we're going to see larger, more destructive storm surges that make it further inland because you're having hurricanes pushing a higher ocean to ever higher and higher levels and further inland. So there's at least 4 distinct ways at this point where the research is very strongly suggestive that climate change is already having an impact on hurricanes and tropical cyclones in general.
Great answer. And I really appreciate that. I love it when people break things out into quantifiable little chunks. So I'm on the opposite coast from Idalia here in Los Angeles. And I can say when I moved here 15 years ago, I was prepared for earthquakes and wildfires. But until just a couple of weeks ago, I hadn't had to think about hurricanes, tropical cyclone, anything like that here in California. So Hurricane Hillary was the first to reach this part of the country in over 80 years. So why is it that tropical cyclones like Hillary don't usually reach California, and what's changed that allows these storms to make landfall?
Yeah, it was pretty striking to see the center of circulation of a tropical storm, Hillary, over downtown LA just a couple of weeks back. That has not happened in, as you say, in decades. The last known landfalling tropical storm in California was in 1939. There have been other tropical storms and hurricanes that came close to California and brought some heavy summer rainfall, especially in the deserts. But actually having one end up in California over populated parts of the LA metro is just exceptionally rare historically. The reason for that is, well, again, I'm going to give you a list of three things, the most important of which is that the oceans are too cool. So if warm oceans are hurricane fuel, California's oceans don't provide very much, if any, of it. The ocean, of course, off of Northern California is genuinely cold in summer. I mean, try going for a swim on Ocean Beach in San Francisco. Now, the water, off of the Santa Monica Pier or the Scripps Pier in San Diego is definitely warmer, but still not nearly warm enough to sustain hurricanes or tropical storms in any meaningful sense. So you really need water temperatures up in the 79, 80 degrees Fahrenheit range to really sustain that. So quite warm oceans, and the oceans just aren't that warm. So there's a lack of fuel, meaning that storms definitely don't form near the coast of California, and those that try and make a beeline for the state rapidly run out of fuel as they do so, and so they weaken rapidly. The second factor is that in the tropics, there are essentially easterly winds, meaning winds that blow from east to west. And that tends to steer hurricanes in tropical ocean basins from east to west. So if you're on the east coast of the United States, where the coast is on the west side of the ocean basin, an east to west steering current is going to push hurricanes towards the coast from east to west. On the west coast of the continent, though, as where California is in the Pacific basin, you're going to have hurricanes that form in the tropics off the coast of Mexico. That's not uncommon. That happens every year. But they tend to get steered westward out over the open ocean rather than toward land. So a few of them make it close to Hawaii out in the open ocean, but most of them end up over essentially the vast unpopulated stretches of the Pacific. So that's reason number two, is the tropical winds tend to steer hurricanes away from California. And the third reason is that the atmosphere itself is just pretty darn hostile to storms, to tropical storms and hurricanes near California. It's too stable. There's not enough moisture above the really shallow, foggy marine layer, so it might feel damp right at the surface on a foggy morning in June. But as you go up higher in the atmosphere, almost all of that moisture is confined to below the height of the mountains. So once you get up high in the atmosphere, there's downward motion, which tends to suppress clouds and storm activity, rather than upward motion, which you'd need for the development of those deep tropical thunderstorm clouds to start to swirl and eventually become a hurricane. And there just isn't enough moisture really either. So you sort of have three factors working against it. The ocean's too cold, the winds blow the storms away, and the atmosphere just wants to tear any storms that try to come here to shreds. So you got to come past all of those three barriers to get a tropical storm or a hurricane in California.
Okay, so one of the things I've learned from my colleagues here at Union of Concerned Scientists is about a concept called vapor pressure deficit, and why that's helping fuel wildfires out in California. We had an episode about it a few weeks back, but is that last point that you made, is that referring to that vapor pressure deficit in any way?
That's a good question. It actually isn't in this case, although I do think the vapor pressure deficit is in some ways the most underappreciated climate change variable of all time. It is. I'm glad you've had a longer discussion on that because it's super critically important. Here, though, I think it's really just a question of there just not being a lot of moisture in absolute or relative terms above California in the summer months most of the time. So it's a largely dry, stable downward motion in the atmosphere. It just acts like a lid, and pretty literally like a lid on a pot, and just keeps those storms from bubbling up. So there's a lot working against hurricanes in California, but apparently not so much that every once in a while a weakening system can't slip through if the conditions align just right, and those one or two of those barrier shields are somewhat reduced for whatever reason.
Great. Thanks for clearing that up. Because we do have a lot of very astute listeners, I figured it was worth asking about that. So I actually grew up in Colorado, and there we had a saying that was, if you didn't like the weather, just wait 10 minutes. And so from a purely anecdotal perspective, and, I just went through yet another heat wave here in LA. It ended last night. It seems anecdotally like weather whiplash is something that more and more people seem to be experiencing. Is this simply due to the El Nino weather conditions that we've got this year, or is this much more complex? I think I know your answer, but I just want to check.
Yeah, I mean, El Nino definitely plays into some of the reasons why, especially the tropics and some of the subtropics are seeing such extreme heat events this summer. But the big picture elsewhere really is more to do with the long-term warming of the climate system, climate change that we're seeing, along with other types of sort of natural variability superimposed on top of that climate change. And I think that, when we talk about weather whiplash, I usually tend to narrow it to hydroclimate whiplash, so thinking about the wets and the dries, because if you think about it, we're not seeing more warmth and more cold. We're just seeing a hell of a lot more warm conditions. So that's pretty one-sided. But when it comes to the hydroclimate, side of things, that's actually it is really there is something interesting going on at both ends of the spectrum. So we are seeing in many places increasingly dramatic swings between wet and dry in a warming climate, and that is that actually all has to do with the relatively basic thermodynamics of the atmosphere. So we all hear about how the atmosphere's ability to hold water vapor increases exponentially, even for a linear warming. So this is I mean this in the strictest mathematical terms. It is 7% per degree centigrade. That's that Clausius-Clapeyron relation, if you've heard of it. The dry side of that is exactly what we talk about, what I'm sure you talked about in the episode with the vapor pressure deficit. Essentially, it increases the atmosphere's ability to demand water from the landscape. But on the wet side, what it's doing is increasing the atmosphere's ability to precipitate at an increased intensity. So both sides of that hydrologic coin, drier dries, wetter wets, mostly being driven by that really basic thermodynamic but exponential thermodynamic reality. And California is kind of an epicenter of this because we have such a narrow rainy season. In a typical year, you don't see significant summer rainfall. Clearly in LA this year, that's not the case. But in a normal year, it wouldn't really rain in summer really at all. But it would consistently rain at least 10 or 20 times, say, in a typical winter. And so there's really only one opportunity to get meaningful precipitation in most parts of California, and that's in the winter rainy season. The spring and the fall are kind of spotty. You can get some precipitation, but it's few and far between. It varies a lot from year to year. The winter is consistently wet. The summer is consistently dry. The transition seasons can go either way. But that means that if you miss out on winter, any given winter being dry, you're out of luck till the next winter. So you're not going to regain that ground in spring or summer or fall. You're going to have to wait at least until the next winter. And if that one's dry, you got to wait a whole nother year. So it's easy to get into droughts here, but by virtue of the fact that much of California is in fact not a desert, and in some parts of California see close to 100 inches of rain a year in the wettest parts of the North Coast and the northern Sierra Nevada foothills. So, California varies from one of the driest places on Earth in Death Valley, a couple inches of rain a year, to nearly 100 inches in the northwestern corner of the state. Huge variability, but that whole state mostly gets its precipitation in the winter. With the exception of a couple of desert areas. And by that, the reason why I bring this up is because it makes California quite susceptible to drought, because there are few opportunities to see that significant precipitation, but because we do live in a part of the world that supports substantial forests and biomes that require a lot of water. You might guess that there are periods where it's actually quite wet, since you got to get the water at some point. If it's dry 3/4 of the year, you're going to have to get quite a lot of water in the quarter of the year that isn't usually dry. And so in winter, we do tend to see these extreme precipitation events, usually associated with storms called atmospheric rivers, these very narrow plumes of super concentrated atmospheric water vapor that look, when you look down from satellites, they look an awful lot like rivers in the sky. There's sort of these sinuous, meandering, corridor-like features where there's just this massive quantity of water vapor getting fluxed into the state above your head. So it's kind of like having multiple Mississippi rivers worth of water vapor moving above your head. And you can imagine that when those Mississippi rivers of water vapor slam into the mountains and the air rises, cools, and condenses, falls out as precipitation, sometimes quite extreme precipitation, well, that's California winter in a nutshell. A lot of the precipitation in many years comes from just a handful of like individual strong storms. So we see this, that these individual strong storms are becoming wetter in a warming climate, but not necessarily more numerous. So there's this notion of increased whiplash there, hydroclimate whiplash, and then the dry seasons are becoming even more intensely dry because of what you've already talked about, this increasing vapor pressure deficit. So the rain is falling more intensely and either as frequently or less frequently, and then the rest of the time when it's not raining, evaporation is more intense. So you're extracting that water that's falling more rapidly, more quickly than back out again out of the landscape.
Okay, so in my field of expertise, geology, we look at past events to help determine what might happen in the future. So, for example, we map ancient volcanic eruption deposits to help us understand potential future hazards from a given volcano. So that helps us create modern hazard maps and risk mitigation plans for populated areas, and it helps us form a basis for modeling of future eruptions. With climate, how do you use evidence of past extreme weather events to gain insight into what we might be facing as we start to feel the effects of human-caused climate change more and more?
Well, I'll preface my response with the caveat that I'm not a paleoclimatologist, because there are actual paleoclimatologists who directly study how the climate of the past, and the past generally meaning the past prior to modern instrumental records, so going back more than 100 or 150 years and talking about hundreds to thousands of years, and maybe even longer than that. So going back even hundreds of millennia in some cases. This certainly helps us inform the context of what we're seeing today. So we can compare the changes we're seeing today to the kinds of changes that unfolded in different climate epochs. One of the alarming things about climate change is that the changes we're seeing today are happening so rapidly relative to anything that we saw historically. Certainly, but also that we've even seen in the paleoclimate record going back thousands of years. So the rate of change, the paleoclimate perspective helps us put that into context. And then more recently, even thinking about the last century or so, we do have actual thermometers and rain gauges measuring things around the world. That helps us understand the record-breakingness, if you will, or whether certain kinds of events are historically unprecedented, which is important in a warming climate because we've adapted a lot of our human systems around the observed maxima of events in the period during which that infrastructure in those cities were built and developed. So, in a lot of cases, we're reliant on 20th century and even 19th century baselines for the world we live in, everything from bridges to dams to buildings to telecommunications infrastructure. A lot of this is based on the climate that was observed in the century or the 50 years leading up to the development of said infrastructure. And we no longer have that climate. And so it's important to understand the degree to which what we're observing today diverges from those historical baselines, partly because it helps us understand the level of impacts that we're seeing today in the real world.
I really appreciate how you tied that to infrastructure, because it's, with our sciences, we always, the sheer intellectual stimulation we get from studying these things is great, but we always have to do our research with the real world impacts in mind. And I think it's really important to make that note that we, human structures, we only have so much in terms of records for how they perform. And we're really seeing a lot of those put to the test. So that actually sort of brings me back to Hurricane Idalia. And I saw online that we currently have not one, not two, but 3 tropical cyclones that were, at least for a bit there, all the same intensity. So I'm not a hurricane expert, and that blows my mind a little bit. But I wanted to ask you if that's actually noteworthy to have that number of storms all going at once.
Yeah, I think it's noteworthy. I don't know the precise statistics, but I think it's especially noteworthy in the context that a strong developing El Nino event, which is what we currently have in the Pacific Ocean, normally suppresses the Atlantic hurricane season quite a bit. So if on its own, El Nino should produce fewer storms in the Atlantic than usual. But I think what we're seeing is that the climate change signal is kind of overwhelming this very large magnitude natural cycle in this context, because a lot of the oceans in these hurricane formation regions in the Atlantic are or have been recently been record warm this year. So there's these counterbalancing things. On the one hand, El Nino should be temporarily suppressing storms in the Atlantic because it usually increases wind shear, which is hostile to development of hurricanes. But simultaneously, we have record warm conditions. So we have a more tropical ocean hurricane fuel than ever observed previously in a year where El Nino should be sort of cutting the tops off of these storms. But what we're seeing sort of is that this record-breaking ocean warmth seems to be at least counterbalancing El Nino, if not outweighing it, which is kind of remarkable because the effect of El Nino is not subtle. It's usually quite dramatic, and this is a year where we're seeing that the long-term warming, this record-breaking warmth, is really sort of an equal magnitude, which is genuinely remarkable.
That really is actually fascinating when you put it like that. To see these, it's sort of a fight between what would usually be prevailing conditions. So that would be influencing what we see. And here we are, we're seeing an influence in a way that I think, well, I haven't noticed something like this before, but obviously it's neat to watch as someone who doesn't have that expertise. And I'm sure your phone has been ringing off the hook as a result. So I just wanted to ask you then, so in addition to the things that have been in the news just recently, so extreme heat and wildfires, hurricanes, what are some other extreme weather events that our listeners should be aware of?
Well, I think in general, I mean, some of the kinds of extreme weather events that are most clearly linked to climate change, almost trivially so at this point, are not that the events themselves are trivial, of course, but that the scientific linkage to climate change is so straightforward, it almost goes without saying at this point, are extreme heat events and extreme precipitation events. And increasingly, though, there are other things too. We've talked about the increasingly clear links between different aspects of hurricanes and climate change. Increasingly, wildfire severity and activity as well, really clear links to climate change in a way that is becoming harder and harder to escape in some regions. So it's probably a shorter list of things at this point that don't have links, to climate change. This summer, I think, has been in the news mainly for extreme record-breaking heat and wildfires. But there's really any other number of things that we could point to as well, where there's just a lot going on right now, really.
That's totally fair. And so asking you for a second to sort of bridge the divide between regular citizen and scientist, do you have any suggestions for us to either prepare for the effects of climate change on an individual level, or ideas about how we can urge our government and major corporations to take meaningful climate action?
Yeah, I mean, I think that my usual line, at this point is that obviously individual actions are important, but I don't, I think the suite of options available to any particular individual varies, depending on your circumstances, where you are in life, where you are in the world, and any number of other things. And I think sometimes people get really hung up on this notion that if everybody went vegan, or if everybody stopped going to airports, that we would magically solve the problem. And I think that kind of misses the broader point, which is that this is a huge global problem that needs systemic solutions. We need to make it easier for people to make good choices, to broaden the range of options that people have, not just in their daily lives, but in the way systems operate. And so I think that individual actions are important to the extent that they sort of act as a vote in society or in the economy, in the direction that we need to move things. But ultimately, I think that the most important thing that individuals can do is to become politically involved, because ultimately climate change it's not like we don't have any idea how to solve the problem at this point. We know at a macro scale, right, exactly what needs to happen. We need carbon emissions to, as soon as possible, go as close to zero as possible. That's essentially, it's literally a one sentence summary. Of course, it's not easy to do that. I mean, obviously, if it were that easy, problem solved, right? But the challenge is that how to do that is not really a scientific question. at this point. It's more of a social and governance question. So therefore, it's essentially a political problem. How do we implement these changes? How do we encourage and foster global systems of energy production, of agriculture, of transportation, of all of these things that don't have this massive negative externality of these carbon emissions that are causing harmful global warming? And obviously things like electrifying our transportation networks and our infrastructure are hugely important steps along that process. But there's so much more that needs to be done still. And I think the changes are so transformative that I think we need better frameworks for understanding and contextualizing and, of course, implementing the kinds of hugely transformative systemic changes that we actually need in across all of these sectors. And so I think it's, becoming involved, whether that's, obviously people talk about voting, which is of course critically important, but then it's also a matter of having conversations with people. The average American claims that they don't hear about climate change in the average week or the average month even. I mean, that's amazing to me in this day, in this summer. Maybe it's changed this summer. I don't think there's any new numbers out since June, but the reality is that's a problem, unto itself. The political parties in the United States are very, among many other things, are out of sync with public opinion on climate change to a very high degree. So there's much less a serious conversation about how to address climate change, at the federal government level than there is, I think, in terms of that's representative of people's belief in climate change. That's actually a much more universal thing in this country, even in this very partisanly divided country. There's more agreement among people that climate change is there and a problem than there is among their elected representatives. So that's a big challenge. There are a lot of things that we can do, to work on that side of things. So I think that because this is such a systemic global problem that's going to require large-scale transformative systemic solutions, I think that it's, being involved in the conversation all the way from the local level up to the highest level that in your life you have you where you have a voice, I think is probably the most important thing that is accessible to the most people in terms of what they can do individually.
I'll just say here to that, because I completely agree. And I think it's a great message to get out there. So we're close to the end here. And since we are the Union of Concerned Scientists, I like to ask my guests one final question. And that would be, Daniel, why are you concerned?
Yeah, well, there's any number of reasons. But as a climate scientist, it would be pretty odd if I were not concerned circa August 2023, just given everything we see unfolding in the world all around us. I will say, I will maybe give a slightly more nuanced answer, which is that what I'm most concerned about today is not that the warming we're seeing is faster than expected, or that it's accelerating in a way that we didn't anticipate or anything like that. My worry is that the warming is almost exactly what scientists had predicted it would be at this level of carbon emissions decades ago. And yet, here we still are, still emitting that carbon, still, on that upward trajectory. And I think what we had not anticipated decades ago with some of those early climate predictions is that we would still be on this trajectory today. We're still on a path to see a lot of additional warming and to see, essentially, even if the warming itself isn't accelerating societal and environmental impacts from that correctly predicted, unfortunately, level of warming. So I think that, the optimism there is that it's a problem that we have the ability to solve, but the concern stems from the fact that we aren't addressing it nearly with the seriousness or urgency that would really be commensurate with the scale of the problem at hand.
Well, I think that you have hit the nail on the head, and I really appreciate that you are one of the folks out there fighting the good fight to get both the research done that we need and also the science communication out so that the public can understand that straight from scientists, this is reality. So thank you so much for carving time out of your busy schedule to sit down with me and have a little chat. And I really appreciate the work you're doing. And thank you so much from me and from all of us here at UCS.
Thanks again for having me.